Hi everyone, so I'm going to go over the practice exam 2 for exam 1, and yeah, let's just get started. So for the first question, it asks that a die is rolled twice, and assuming that the die is fair, what is the probability that the two rolls show different numbers? So for this we're looking at the probability that given the two rolls, we're looking for the probability that each roll has a different number. So this is the same as the probability that 1 minus the probability that they have the same number. And so if we look at different combinations, so we have 6 different combinations of the die having the same number, which are if it's 1, 2, 3, 4, 5, 6. So now that we know that, we can go ahead and solve this problem. So the probability of having the same roll would be, so for each dice roll, it's a 1/6 probability for each number, and then since we're rolling it twice, we multiply that by another 1/6, and then since we have 6 different possibilities, we can multiply it by 6, and this is 1 minus all of that. So that would be 1 minus 1/6, which is equal to 5/6. And that's our answer, so this over here. Okay, so next we have if the die is based such that it's basically an unfair die where these are the probabilities here, what is the probability that the maximum value to appear in the two rolls is 6? So what we're calculating is the probability that either roll 1 is 6 or that roll 2 is 6. Since if either roll is 6, then the maximum value will be 6. So we can use the union rule thing, where basically if you have the union of two probabilities, that is equal to one of the probabilities plus the other probability minus the probability of both happening together, and that's to subtract any double counting. So we have that, and now we can solve that. So the probability of it to roll a 6 we have here is 1/3, and then another 6 is another 1/3, and then for both of them to roll a 6, that would be 1/3 times 1/3, so that would be that'd be 2/3 minus 1/9. 2/3 is the same as 2/3 is the same as 6/9 minus 1/9, and that equals 5/9. So that is our answer here. Okay. So now we want to consider a situation where, so this scenario here in problems 3 to 5, so the probability that an agent possesses psychic abilities is 1 out of 500. So we have our prevalence here, and then we have our sensitivity here, and we have the specificity here. Okay, so now we're trying to find the probability that, so if we tested a non-psychic agent, what is the probability that we get a false positive result? So we're looking for the probability of a positive result given that the agent is non-psychic. So that's the same as 1 minus the probability that the agent gets a negative result and is non-psychic. And we already have that over here, so here it says that the probability that a non-psychic agent is correctly identified, so correctly would be that they tested negative, would be 0.85. So we can just do 1 minus 0.85, and that equals 0.15, which is this answer over here. Okay, now we're testing 30 non-psychic agents, and we're looking for the probability that at least one of them is identified as a psychic. So what we can do is we can find the probability that all of them test negative since they're non-psychic, and then subtract that by 1 to find, or subtract that from 1 to find the probability that at least one of them is identified. So we have 1 minus the probability of all of them identifying as negative, so this would just be 0. So we have our probability of our non-psychics being identified correctly over here, so that's 0.85, so it should be 1 minus 0.85, and then to the power of 30 since there are 30 agents, and that equals 1 minus 0.0076, which is equal to 0.9924. And that is our answer over here. And so that's the probability. So 0.0076 is the probability that all of them test negative, and then 0.9924 is the probability that at least one tests positive. Okay, so what is the probability that an agent has psychic abilities given that their test result was negative? So here we're looking for the probability of the agent being psychic given that their test result was negative. So we can use Bayes' rule here. So this is equal to the probability of the agent being psychic and having a negative test result over the probability of them having a negative test result, which is equal to the probability of having a negative test result given that they're psychic times the probability that they are psychic, and the probability all divided by the probability that they have a negative test result. And so first we need to find what this value is. So this is the probability of getting a negative test result. So that is equal to the probability of a negative test result given that they're psychic times the probability that they're psychic plus the probability of getting a negative test result given that they're not psychic times the probability that they're not psychic. Okay, so, and then we have all our probabilities in the problem. So the probability that they're negative given that they're psychic. So we have here, given that they're psychic, the probability of accurately identifying it is 0.97. So the probability of inaccurately, or having a negative result would be 0.03. And then here we have the probability of being a psychic is 0.002. And now we need the probability of testing negative and being non-psychic. And that's given over here, so that's 0.85. And then the probability of not being a psychic is just 1 minus 0.002, so that is 0.998. And all of that put together should be equal to 0.8484. And then now we can plug in those values into our Bayes theorem equation. So we have the probability of a negative result given that the agent is a psychic. So given that the agent is a psychic, the probability of a positive result is 0.97, so negative is 0.03. And then we have the probability of being a psychic, so we know that one was 0.002. And the probability of a negative test result from what we just solved, which is 0.08484. And then all of that together equals 0.00007. So very small number, but that's our answer. And yeah. Now we have box plots. So they summarize a recent statistics exam taken by two different classes, Class A and Class B. So first, it asks us how many outliers are present in Class A. So outliers are basically any of these little dots that are outside of the box plot. So here's only one dot, so that means there's only one outlier here. Which statement is the best interpretation of the box plots? So we have Class A has a higher median score but greater variability. Class A has both a higher median score and lower variability. Class B has a higher median score and more outliers. And both have identical means and variabilities, or none of the above. Okay, so let's compare their median scores. So the median score is basically this thing over here. So this is for Class A, and since Class A has a higher median score, a higher median score, we know that A has a higher median score. These can be correct. This has to be wrong since this is not true. And this is also not true. Okay, now we can look at variability. So variability can be measured by basically how grouped together the data is. So since like all of these lines here, like it's all close together, these are the quartiles, first quartile and third quartile, they're both very close together, whereas for Class A, they're further apart. So we can say that A has more variability. So has median score and greater variability, but not the lower variability, so we know that A is the correct answer. So suppose that the teacher wanted to award a prize to the class with the most consistent performance, less variability. Which class should be chosen? So as we've already seen, Class A has more variability than Class B, so if we're looking for less variability, then Class B, because its scores are more tightly clustered around the median. So that's how we tell that it has less variability. Okay, so now we have our free response questions, and I'm just going to take a little short break, and I'll be right back. Okay, so now we'll go through the free response questions. So our first question says that 2 coins are to be flipped, and the first coin will land on heads with a probability of 0.6, and the second with a probability of 0.7. Assume that the results of the flips are independent. So we have our distributions here, and so it's asking us to construct a joint probability mass function of x1 and x2. So to start, we can find the probabilities, so the possible pairs the possible pairs of values that we can have for x1 and x2. So our possible values would be 0, 0, 0, 1, 1, 0, and 1, 1. Okay, so now we can find the probability for each of these, the joint probabilities. So we have the probability of x1 equals 0 and x2 equals 0. So that's our first one here. And so since they're independent, as stated here, we can just multiply the probabilities. So we have, for the first coin, it's a 0.6 probability of getting heads and a 0.4 for getting tails. And then here it's 0.7 and 0.3. Okay, so for getting 0 for both, which are tails, we would have 0.4 times 0.3, which is equal to 0.12. So then we have our probability of x1 equals 0 and x2 equals 1. And that would be 0.4 times 0.7. That equals 0.28. And then we have our probability of x1 equals 1 and x2 equals 0. And that would be 0.6 times 0.3. And that would be 0.18. And then we'd have our probability of x1 equals 1 and x2 equals 1. And that's our last thing here. So that would be 0.6 times 0.7, and that would be 0.42. And those are our joint probabilities. So now we need to solve for the variance of x. So since they're independent, our variance of x will be equal to our variance of x1 plus our variance of x2. And so since that our trials are independent and we have success or failure, so success is heads and failure is tails, and we have a constant success value, so each of them have different values, but they're both the same trial. So it's still a constant success value, or if we talk about them individually, our p-value here is 0.6 and our p-value here is 0.7. So because of that, these are Bernoulli distributions. So we can use the formula for our variance for Bernoulli distributions, which is equal to the probability of success times the probability of failure. So now we can solve using that. So for our first, for x1, our probability of success is 0.6, and our probability of failure is 0.4. And then we can add x2, so that's probability of success is 0.7 times the probability of failure, which is 0.3. And then that would be 0.24 plus 0.21, which is equal to 0.45. And that would be our answer. Okay. So for the next problem, we have our probability density function for a certain type of electronic devices, and it's given by this function. So first we want to find the probability of x being greater than 20. So here we need to find the integral of from 20 to infinity of our function f of x dx. And so since this is since it's going to infinity, we can use limits. So we can do limit as n goes to infinity of 20 to n, and then it'd be of 10 over x squared dx. And so this is equal to, again, the limit of n to infinity, negative 10 over x, and then from 20 to n, and then let's go here. This would be equal to the limit of n to infinity of negative 10 over n plus 10 over 20. And as n goes to infinity, the denominator here will just keep getting bigger and bigger, so this entire fraction will go to 0, which makes this equal to 0.5. Okay, and then now it's asking for the cumulative distribution of our function. So recall that the formula for a cumulative distribution is f of x is equal to the integral from negative infinity to x of f of t dt. So now we can plug in our function. So in our case, it'll be, our lower bound will be 10, since x has to be greater than 10, and then our upper bound will be x. And then we have 10 over t squared dt. Okay, and then we have, this would be equal to negative 10 over t from 10 to x, and then this would be equal to negative 10 over x plus 10 over 10, and that is equal to 1 minus 10 over x, where x is greater than 10, and if x is equal to 10, then our value would just be 0, so we can also say that x is greater than or equal to 10. Okay. So what is the probability that of 6 such types of devices, at least 3 will function for at least 15 hours? So since we're having 6, this is like 6 trials, so this becomes a binomial kind of problem, binomial distribution. So we can say that y is the number of devices out of the 6 that function for at least 15 hours. So that can be binomial 6, and then we have 2/3 is the probability, okay, so actually we should calculate this first. So first let's calculate the probability that one device will last over 15 hours. So we have a probability of x is greater than or equal to 15. So that is equal to the integral from 15 to infinity of f of x dx, and that's equal to the limit of n goes to infinity of 15, the integral of 15 to n of 10 divided by x squared dx. Oh, okay. And then that is equal to the limit of n goes to infinity of negative 10 over x from 15 to n, and that way over here equals the limit of n goes to infinity so we have our negative 10 over n plus our 10 over 15. And as n goes to infinity, this gets really large in the denominator, so this goes to 0. Okay. And then that just leaves us with 10 over 15, which is the same as 2 over 3. Okay, now we can make y equal to the number of devices that out of the 6 that function for at least 15 hours. So y can be binomial 6, and then 2, 3 is basically, 2, 3 is the probability of success. And our q is the probability of failure, so that's 1 minus p, and that's 1 minus 2 over 3, which is 1 over 3. Okay, so we have our values here. So now let's solve for the probability of at least 3 devices functioning. So we can do that by finding the probability that only 0, 1, or 2 devices will function, and then subtract that from 1. So we can do that by, so our probability of y being greater than or equal to 3 is 1 minus the probability that y equals 0 minus the probability that y equals 1 and minus the probability that y equals 2. And then we can solve for the probabilities. So since these are binomial, this is a binomial distribution, we can use the binomial formula. Okay, so our binomial formula, as we recall, is p, so x equals some value. I should move this. There. So it's if it equals some value, so we have nk, where n is the number of trials and k is the number of successes, and then times p, so this is the probability of success to the power of k, times 1 minus p to the probability of n minus k, and this is probability, 1 minus p is probability of failure, and n minus k is n minus k, the number of, Okay. So yeah, that's a number of failures. And then now we can use that here. So we have 6 trials. Okay, so we have our 6 trials, and then here we'll have 0 successes, and then we'll multiply it by our p-value is 2/3, probability of success times the number of successes, that's 0, and then times the number of failures or 1/3 to the power of the number of failures, and that is, that should be all 6. Okay, and then we have, for 1, we have 6, choose 1. So the probability of success is 2/3 again, so we have 1 success. And then we have 5 failures. And then our last one is 2 successes, so 6, choose 2. Probability of success is 2/3. And probability of failure is 1/3. So that would be 4 to the power of 4, because 4 failures. Okay, and then we just need to solve for all of this. So 6, choose 0, so that's just 1. Then to the power of 0 is also 1, so it's just 1/3. 1/3 to the power of 6. So that would be equal to 1/729 minus 6, choose 1. So 6, choose 1 would just be 6 times, I should give myself some space. Okay, so this would be 6 factorial divided by 1 factorial times 6 minus 1 factorial. So that would just be equal to 6. And then times 2/3 times 1/3 to the power of 5. And so all of that together would be equal to I am not a fan of calculating this on the spot, but it is fine. Actually, I'll just do 12 over, yeah, okay, so that'll just be 12 over, I think it should still be over 729. Okay, and then next we have over here, so we have 6, choose 2, so that would just be 6 factorial, 2 factorial, 6 minus 2 factorial. And so this would basically just be, so this would be 4 factorial over here, so it'd be 6 times 5 divided by 2, which is equal to 15. And then times 2/3, so that's 2/3 squared times 1/3, 4, to the power of 4. Okay. And then, so if we multiply all of that together, so we've got 4 up here, 4, and times 15, so that would be, I believe 60, and then the denominator would still be 729, since it would be 3 to the power of 6. Okay, yeah. And then if we do the math here, so we have 729 minus 1 minus 12 minus 60. So that equals 656 over 729, and that is approximately equal to 0.9, and that is our answer. Okay, so question 13. So we have our distribution function of x, and we want to find the probability mass function and the probability density function of x. So this function has some continuous parts and some discrete parts. So we need to find the probability mass function for our discrete parts and the probability density function for our continuous parts. So let's start with finding our continuous parts. So our continuous parts are so this is our cumulative distribution, and our continuous parts are where we have our b here, so it's like changing during this interval. So these two are our continuous parts. So our range is 0 to 1 and 1 to 2. Okay, so now we can calculate our probability density function for our continuous parts. So we do that by finding the derivative of our continuous parts. So we have, for this, we have our first one for 0 to 1 is d dB of b over 4, and that would be equal to 1 over 4. And then we have our derivative for our other function, so this part, so that's 1 over 2 plus b minus 1 over 4, and that is also equal to 1 over 4. So we can conclude that the continuous part of our function would just be equal to, so f of x would just be 1 over 4, and then for our range where x is greater than or equal to 0 and less than 2. Okay, so now that we've got our probability density function, we can solve for our probability mass function of our discrete points. So let's find our discrete points. So our discrete points will be where we have jumps in our function. So we have over here where this range goes from 0 to b is less than 1. So when b is 1, this part is 1, 4. But since that's not included, we jump over here, and then when b is 1 here, that's 1/2. So This might be a little confusing to explain like that, so let me just go through the problem. So we have our jump discontinuity at px equals 1, and so we can solve that by just plugging in 1 into both of these, because this would be basically, this is the values before 1, and this is the value after 1, and so, or during 1, I guess. And then if we just subtract it, we can find the value of 1, if that makes sense. So we have, if we plug in 1 here, we have 1 over 2 minus 1 over 4, and so that just gives the value of 1 over 4. And then we do the same for everything else. So we have p x equals 2, and we have our values here. So this is before 2 and during 2. So that would be 2 minus 1 is 1 over 4. So that'd be 3 over 4. Oh no, sorry, we need to do this one first. So this is 11 over 12 minus 3 over 4. And then if we multiply that, so that would be 2 over 12, which is also equal to 1 over 6. And then we have our last one, so that one's p, where x is 3. So once again, we have before and during are 3, and then that one's just 1 minus 11 over 12, which is equal to 1 over 12. And that is our probability mass function. Okay, so now we need to find probability of probability of where x is greater than 2. So to solve for this, all we really need to do is find, so since this is a cumulative distribution function where b equals 2, the values over here contain the values at the probability at b equals 2 and all of the probabilities from before it. So what we need to do is take 1 minus f of 2. Since this is a cumulative distribution function, and yeah, each of these contain all of the values, so that way the end is 1 because it contains all of the values from before, if that makes sense. So we have 1 minus f of 2, and so over here we have f of 2 is 11 over 12, so that would just be 1 minus 11 over 12, and that equals 1 over 12, and that is our answer. Okay, and then now we need to find the median of x. So our median is the 50th percentile. So basically what we're looking for is the value of b when our cumulative distribution function is at 0.5, since that would be the 50th percentile. So first we can try b is, if we try b is less than 1, we get this here. So if we have b is less than 1, we have around 1 over 4, so this is the 25th percentile. And then since we're looking for the 50th percentile, we need to keep going, so now we have b is equal to 1. And this isn't the exact value since it's less than 1, so technically we wouldn't be plugging in 1, we'd be plugging in like 0.99, but it's close to the 25th percentile. So then we have b equals 1, so then if we plug that into our function here, so then we get 1/2, which is in fact the 50th percentile. Promise my handwriting is better normally. But yes, so then b equals 1 is the answer. So that is our median, because our median is our 50th percentile. Okay, so now we need to find variance. So our formula for variance, if you recall, is, so our variance of x would be equal to our expected value of x squared minus our expected value of x, the square of our expected value of x. So essentially this. And so first we need to solve for our expected value of x. And that basically would be, so since our distribution isn't completely continuous, what we would have to do is we'd have to separate each of our parts, since it's like a piecewise, and then add them up all together. So we need to find the mean of each part and add them together. So here we have from our first range, so 0 is just 0, then we have 0 to 1, so 0 to 1, and then we have x over 4, and then our next range is 1 to 2, and for that we have oh, actually we can use our hold up, we can use our joint probability functions, actually. That works better. So we have, we already have here that for 0 to 2, we have x over 4, so for both of these. And then now we can add our point distribution. So since we already calculated that, we can just use it from here. So when we have x equals 1, we can just do 1 times, and then our value would be 1.4. So when x equals 1, that's 1.4, then plus when x equals 2, we have times 1.6, and then we have when x equals 3, we have times 1.12, 1 over 12. Why did I say point? 1 over 12, 1 over 6, yes. Okay. And then if we add all of this together, we should get 4 over 3. And then now we can do the same thing for x squared. So basically we just calculate it all the same way, but we square x. So there's that. 1, 2, x squared dx. And then these are our x values over here. So we're just gonna do them all squared. And then we should get 7 over 3. And now we can plug it into our variance formula. So that would be 7 over 3 minus 4 over 3 squared. And that would be 7 over 3 minus 16 over 9. And then 7 times 3, it's 21 over 9 minus 16 over 9. And that is equal to 5 over 9. And that is our answer. And that is practice exam 2. I really hope this helped. And if you have any questions, feel free to come to my office hours. Okay, thank you guys. Bye.